Today we're going to talk about one of the biggest ideas in chemistry, the mole. And I know it can sound a little tricky at first, but trust me, by the end of this, you'll see it's really just an incredibly clever way to count things you could never, ever see.
All right, let's just dive right in with the huge problem that chemists were wrestling with for centuries. It's a question that honestly seems completely impossible to answer.
I mean, really think about that for a second. If I gave you a diamond, could you tell me exactly how many carbon atoms are in it? Or, if you picked up a 1 kilo iron weight, could you count the atoms? No way, right? They're just ridiculously small, and there are billions upon billions of them. But here's the catch. All of chemistry depends on knowing those numbers.
You see, chemical reactions aren't just random stuff happening. They're like super precise recipes. You need a specific number of atoms of one thing to react with a specific number of atoms of another. So, how are you supposed to follow the recipe if you can't even count your ingredients? That was the big challenge.
So to solve this massive puzzle, chemists came up with this brilliant idea. And to get our heads around it, we can actually just look at something we all use every day without even thinking about it.
Let's talk about apples. If you ask for a dozen apples, you know exactly how many you're getting, right? 12. It's a fixed number. But the total weight? That's going to change every time. On the other hand, if you buy a kilo of apples, you get a fixed mass, 1 kilogram. But the number of apples you get will be different depending on how big they are. So one way gives you a fixed count, the other gives you a fixed mass.
And right there, that's the million-dollar question. What if you could invent a unit that gave you the certainty of a dozen? You always know the number, but was also tied to a predictable, fixed mass, like a kilogram. What if you could create something that bridges that gap between counting and weighing?
Well, that's it. That's the mole. It is the solution to the whole problem. It's this special quantity, this specific amount of stuff. You can totally think of it as the chemist's very, very, very big dozen. It lets scientists work with amounts they could actually see and weigh, like in grams, while knowing exactly how many tiny particles they're playing with.
So, if a dozen is 12, what number is a mole? Well, this is where your brain might start to melt a little bit. Because the number we're talking about is so outrageously big, it's actually hard to wrap your head around.
There it is, 6.022 times 10 to the 23rd power. That is a 6 followed by 23 zeros. I mean, just try writing that out. This isn't just a big number, it's an absolutely astronomical number.
And this magical, massive number has a name. It's called Avogadro's number. And it's named in honor of an Italian scientist, Amedeo Avogadro, whose work really helped pave the way for this idea. It is the exact number of particles, whether we're talking atoms or molecules, inside 1 mole of anything.
And this picture shows you its power perfectly. So in that beaker, you've got 12 grams of carbon powder. It's something you can hold, you can weigh, it's real. But because we understand the mole, we know that inside that powder, there are exactly 6.022 times 10 to the 23rd carbon atoms. 1 mole of carbon is 12 grams. The invisible is made knowable through the visible. It's amazing.
Okay, let's keep going and really unpack how this incredible link between a weighable mass and a fixed number of particles actually works for all the different elements.
The secret here is a concept called gram atomic mass. And honestly, it sounds way more complicated than it is. All you do is look up an element's atomic mass on the periodic table, that little number on there, and then just measure out that same number, but in grams. And boom, that amount right there is 1 mole of that element.
This table makes it crystal clear. So, carbon's atomic mass is 12 units. That means 1 mole of carbon weighs 12 grams. Oxygen's atomic mass is 16, so 1 mole weighs 16 grams. Iron is about 56, so a mole of iron weighs 56 grams. You see the pattern? The periodic table isn't just a list of elements, it's a cheat sheet for weighing out moles.
Okay, so here's the absolute key point, the one thing you really need to get. 1 mole of anything always, always, always has the exact same number of particles, Avogadro's number. The mass for each one is different, but it's predictable, 12 grams for carbon, 56 for iron. But the particle count, it's always the same. It is the perfect bridge between weighing and counting.
All right, so we've got this gigantic number and this really clever system for weighing things out. But so what? Why is this such a big deal? Why is the mole one of the most important ideas in all of science?
It matters because the mole is the ultimate bridge. It connects the world we can see and touch, the macroscopic world of labs and scales and powders, with the microscopic world of atoms and molecules, which is where all the real chemical action happens. It lets us control the invisible by measuring the visible.
And its use goes way beyond just chemistry. Biologists need it to figure out the atoms in huge molecules like chlorophyll. Physicists use it in their theories about how gases work. And pharmacists? They absolutely depend on it to make sure drug dosages are precise and safe. The mole is truly a universal tool for science.
Before we wrap this up, I want to leave you with one last thing, just to try and give you a sense of the mind-bending scale of Avogadro's number. It's one thing to see it written down, it's another thing to feel it.
Just let that sink in for a moment. If you had 1 mole of rupees, you could make every man, woman, and child on planet Earth a trillionaire. That's the kind of scale a chemist is dealing with in just a handful of powder. It's a number that connects our world to the atomic universe in the most profound way possible. And it really makes you wonder, what other incredible connections are out there, hiding in plain sight?